the 2 by 2 inverse formula. Every linear algebra student memorizes it. For a matrix with entries A, B, C, D, the inverse equals 1 over AD minus BC times the matrix with D and negative B in the first row and negative C and A in the second row. You swap the diagonal entries, negate the off-diagonal entries, and divide by the determinant, AD minus BC. But look closely at the result. Right? Every entry in that matrix is a cofactor of the original, a signed minor determinant. Notice the checkerboard sign pattern, plus, minus, minus, plus. This is not a coincidence. The same pattern generalizes to every invertible matrix, 3 by 3, 4 by 4, even 100 by 100. And the proof of why it works is one of the most elegant arguments in all of linear algebra. Take the matrix A, B, C, D. Its inverse is 1 over AD minus BC times the matrix D, negative B, negative CA. Now let's see where that formula comes from. By computing cofactors, the cofactor Cij equals negative 1 to the power I plus j times the determinant of the submatrix remaining after deleting row I and the column j. Let's compute each one. C11. We delete row 1 and column 1 from our matrix, leaving the single entry D. The sign factor is negative 1 to the power 1 plus 1, which is positive, so C11 equals D. C12, we delete row 1 and column 2, leaving the entry C. The sign factor is negative 1 to the power 1 plus 2, which is negative, so C12 equals negative C. C21, we delete row 2 and column 1, leaving B. The sign is negative 1 to the power 2 plus 1, which is negative, so C21 equals negative B. C22, we delete row 2 and column 2, leaving A. The sign is negative 1 to the power 2 plus 2, which is positive, so C22 equals A. Now we assemble the cofactor matrix C. It has rows D, negative C in the first row, and negative B, A in the second row. Next, we transpose it. C transpose is D, negative B in the first row, and negative CA in the second row. Notice that is exactly the matrix appearing in the inverse formula. So the 2 by 2 inverse is 1 over the determinant of A times C transpose. This generalizes to any n by n matrix. We define the cofactor matrix C, where Cij is the cofactor of Aij. The inverse formula is inverse equals 1 over det A times C transpose. Here, A is the original n by n matrix, det A is a scalar, C is the cofactor matrix, and C transpose is the transpose of C. The transpose is critical. Without it, the proof breaks down. Notice the entry I, j of C transpose equals Cji. So position I, j of A inverse, contains the cofactor of Aj, not Aij, precisely because of the transpose. Let's see this in action with a 3 by 3 example. Consider a 3 by 3 matrix A with symbolic entries Aij. We'll compute the cofactor C23. First, delete row 2 and column 3 from A. This leaves a 2 by 2 submatrix consisting of A11, A12, A31, and A32. Next, take the determinant of this 2 by 2 submatrix, which gives A11 times A32 minus A12 times A31. Now apply the sign factor, negative 1 raised to the power 2 plus 3, which equals negative 1 raised to the fifth, which is negative 1. Finally, multiply the determinant by this sign factor. The cofactor C23 equals negative times the quantity A1, 1 times A32, minus A1, 2 times A31. Notice the algebraic structure hiding here. Let's build the comparison table. For a 2 by 2 matrix, the determinant of A is the sum of products of 2 entries, but each cofactor is just a single entry, a product of 1. Now for a 3 by 3 matrix, the determinant of A is a sum of products of 3 entries, 1 from each row and column. But each cofactor is a 2 by 2 determinant built from products of 2 entries, And in general, for an n by n matrix, the determinant has products of n entries, while each cofactor has products of n minus 1 entries. Now look at what this means for the inverse formula. In A inverse equals 1 over det A times C transpose, the algebraic sizes balance perfectly. The denominator det A contributes products of n entries. Each cofactor in the numerator contributes products of n minus 1 entries. So every entry of A inverse is a ratio, an n minus 1 sized determinant divided by an n-sized determinant. This is deep structural information that row reduction completely hides. We have a formula. Now let's prove it. The goal is to show that A times C transpose equals the determinant of A times the identity matrix. Let's see what this looks like explicitly for a 3 by 3 matrix. The right-hand side, determinant of A times the identity, gives us a matrix with determinant of A on every diagonal entry and 0 everywhere else. So there are really two things we need to verify. First, that the diagonal entries of A times C transpose all equal the determinant of A. And the second, that the off-diagonal entries all equal 0. Now here's the key logical chain. If we can establish that A times C transpose equals determinant of A times the identity, then we simply divide both sides by the determinant of A. This gives us A times 1 over determinant of A times C transpose equals the identity matrix. And that confirms exactly what we wanted. Inverse equals 1 over the determinant of A times C transpose. Let's start with the diagonal entries. The 1, 1 entry of A times C transpose is computed by taking row 1 of A and dotting it with column 1 of C transpose. Now, what does column 1 of C transpose contain? It holds C11, C12, and C13, and these are the cofactors from row 1 of A. That's because of the transpose. Row 1 of the cofactor matrix becomes column 1 of C transpose. So the dot product, term by term, gives us A11 times C11 plus A12 times C12 plus A13 times C13. But look at this expression carefully. This is exactly the cofactor expansion of the determinant of A along row 1. So it equals that of A. The same logic works for every diagonal entry. For the general case, row I dotted with column I of C transpose gives us row I of A dotted with its own cofactors. This produces the cofactor expansion of the determinant along row I, which always equals det of A. So every diagonal entry of A times C transpose equals det of A, exactly what we needed. Diagonal entries, check. Now for the key insight, the off-diagonal entries, let's compute the 1, 2 entry of A times C transpose. That's row 1 of A dotted with column 2 of C transpose. Column 2 of C transpose holds the cofactors of row 2, C21, C22, C23. So the dot product is A11 times C21 plus A12 times C22 plus A13 times C23. Notice what's happening. So we're using row 1's entries but row 2's cofactors. Here's what this secretly computes. Construct a new matrix, take A and replace row 2 with a copy of row 1. The cofactors of row 2 are unchanged because they depend only on entries outside row 2, which haven't changed. So expanding this new matrix along row 2 gives exactly A11 times C21 plus A12 times C22 plus A13 times C23. That's our dot product. But this fake matrix has row 1 appearing twice. 2 identical rows means the matrix is singular and its determinant is 0. Therefore, the 1, 2 entry of A times C transpose is 0. Right? Every off-diagonal entry follows the same pattern. For I not equal to j, row i's entries times row j's cofactors computes the determinant of a matrix with 2 identical rows, and the determinant is always 0. Here is the complete picture. We show the 3 by 3 result matrix for A times C transpose. The diagonal entries each equal det A. Because each one is a cofactor expansion along its own row, The off-diagonal entries all equal 0 because each one computes the determinant of a matrix with two identical rows. Therefore, A times C transpose equals det A times the identity matrix. Now we reach the payoff. Divide both sides by det A. A times 1 over det A times C transpose equals the identity. This tells us that A inverse equals 1 over det A times C transpose. And with that, the cofactor formula for the inverse is proven. This formula reveals structure that elimination hides. Every entry of A inverse is a ratio of two determinants, a cofactor in the numerator and the det A in the denominator. Let's box our general formula at the top. A inverse equals 1 over det A times C transpose. Now let's unpack what this really means structurally. Each entry of A inverse equals a cofactor divided by det A, which is a ratio of determinants. This immediately leads to two powerful consequences. First, it leads directly to Cramer's rule for solving linear systems. Second, it tells us that if A has integer entries, then every entry of A inverse is an integer divided by dta. Why? Because cofactors are determinants of submatrices with integer entries, so they must be integers too. Now, come back to the 2 by 2 formula we started with, the inverse of the matrix with entries A, B, C, D equals 1 over AD minus BC times the matrix with entries D, negative B, negative C, A, swap the diagonals, negate the off-diagonals, divide by the determinant. That simple recipe was never just a trick to memorize, it was the cofactor formula all along, a shadow of something much deeper. The general formula A inverse equals 1 over det A times C transpose is the complete picture.